So far, we have covered mass spec, which looks at masses and molecular formulas. We've also covered IR spectroscopy, which can look at bonds in a molecule. So our last section for spectroscopy will be nuclear magnetic resonance, or NMR spectroscopy. And NMR is extremely powerful. It can tell us a lot about the structural information about organic compounds. Now, NMR itself involves the interaction between electromagnetic radiation, or light energy, as well as the nucleus of an atom. So we're going to focus a lot on individual atoms that make up an organic molecule. Now, in order to be analyzed by NMR, the atoms must contain an odd number of protons and neutrons, or essentially an odd mass number. We're going to focus on two different atoms. We will focus on proton NMR, which will focus on hydrogens in a molecule. Hydrogens have one proton and no neutrons, so it has an odd mass number of 1. We will also take a quick look at carbon NMR. With carbon NMR, we're going to focus on the isotope carbon-13. Now, the more abundant isotope is carbon-12. So carbon-13 is only present in about 1% of carbon atoms, but this is the only carbon atom that is capable of being read by an NMR. Atoms with an odd mass number have a magnetic moment. And essentially what that means is it has a north pole and a south pole around its nucleus, and it's going to cause it to spin in a particular direction. Now, the nuclei of these atoms can spin in any direction that they want. And so here we have an example of a bunch of different atoms with different spins. Now, this is an example of these atoms in the presence of no external magnetic field. So in this case, when they're just operating freely, they can spin in any direction. Now, if we take these atoms and we apply an external magnetic field, so put it in the presence of a strong magnet from, let's say, a machine, what happens is these spins are going to align with the magnetic field. Now they're going to line up in the direction. However, if the spin is going and pointing in the same direction as the magnetic field, this is called the alpha spin state. If we have a spin that is aligned but pointing in the opposite direction of the magnetic field, this is called the beta spin state. Now, an individual atom can either be in the alpha spin state or the beta spin state, and in fact, it can flip back and forth. Now, the alpha spin state, since the alpha spin states are aligned with the external magnetic field, have a lower energy level than the beta spin state. Even though the beta spin state is aligned, it is pointing in the opposite direction of our applied magnetic field. So what happens in an NMR is we put a molecule containing these atoms in the machine. The machine will apply the magnetic field and align the atoms in the molecule either in the alpha or beta spin states. Then what happens, the machine supplies energy to the molecule. Once the energy is given to the molecule, the atoms that are currently in the alpha spin state can absorb that energy and graduate up to the beta spin state. Once it's up here, it can fall back down and release the energy that it has absorbed. So this delta E is key. This is the energy that the NMR machine measures. So the term nuclear magnetic resonance, what it means is we're focusing on the nucleus of an atom that contains a magnetic field. The resonance is the ability to flip back and forth between the alpha and beta spin state. So we will see what affects this delta E, and it has to do with the type of electronic environment that surrounds the atom in question. So in this picture, we're going to focus on a proton. Now, a proton itself has its own magnetic field. So this electron density comes from the electrons that are occupying a sigma bond to this particular proton. Now, this electron density can influence how the external magnetic field affects the nucleus of this proton. So in general, the more shielded a nucleus is with electron density, the smaller the alpha-beta energy gap. What that means is there's going to be a very small gap and a lot less energy required to have the proton flip between the alpha and beta spin state. So less energy is required. And we get a smaller delta E. Now, ultimately, what we will learn is a smaller delta E leads to a lower chemical shift. Which we will talk about in just a little bit. Now, an NMR spectrum can tell us four main things about the molecule that is being analyzed. Down here we have an example of what an NMR spectrum looks like, and in particular this is a proton NMR, so it's focusing on the hydrogens that occupy the molecule. Now, the four things that an NMR spectrum can tell us. They can tell us the number of signals that occur in the molecule. This is going to correspond to the number of different types of hydrogens we have in the molecule. We can also analyze the signal location or shift. That's the chemical shift. So where on this x-axis the peak actually appears. This signal location is going to tell us a lot about the electronic environment surrounding that particular proton. We can also look at the signal area or the area under the peaks. This is known as the integration, and the integration can tell us how many hydrogens we have of that particular type. And finally, we can focus on the signal shape, which is also known as the splitting pattern. So if we take a look here, we have a peak that is broken up into multiple little pieces. These splits are caused by neighboring hydrogens, and you can actually determine how many neighbors we have from the splitting that occurs. When it comes to the number of signals you would expect in an NMR spectrum, the way that I like to think about it is that protons that have different stories, or essentially different ways to describe them, are different sets of protons which will ultimately give different signals in the NMR. So we're going to go through all three of these molecules and answer the number of signals we would expect to find in the proton NMR for each one of these. So first thing I like to do is draw on the hydrogens that we cannot see in the bond line structure. Now we have a hydrogen bound to the oxygen here that we can see, but we have two on this carbon here, 1, 3 on this end, and another 3. Now, the hydrogen that is bound to the oxygen is obviously its own type. There's no other hydrogen in this molecule that is directly bound to an oxygen. So we'll go ahead and call this one type A. Next, we have a set of two hydrogens. Now these hydrogens are bound to a carbon that is bound to an oxygen and another carbon. There's no set of two hydrogens with this exact same description. So these are their own type and would give their own signal. So we'll go ahead and call these B. Next we have a single hydrogen here that is bound to a carbon, which is bound to 3 other carbons. There's no other hydrogen in this molecule with that exact same description. So go ahead and call this C. Now lastly, we have these 3 hydrogens and these 3 hydrogens. Now these ones are bound to a carbon, which is bound to this particular carbon containing hydrogen C. These 3 are also bound to a carbon that's bound to the carbon containing hydrogen C. So these two have the exact same description, which makes them the same type of protons. So we have 4 types, which means we would expect 4 signals. Moving on. We have a molecule. We have 3 hydrogens on the end. We have a single hydrogen bound to this carbon of the double bond and another hydrogen to the other side. We have 2 and another set of 3. So we'll start off with these 3 hydrogens. These 3 are bound to a carbon, which is directly bound to the double bond. So these guys are 1 bond away from our double bond. These 3 are different than these 3 because these 3 hydrogens are 1, 2 bonds away from our double bond. So they have different descriptions, which makes them 2 separate types. So we'll go ahead and label A and B. Now we have a hydrogen bound to the double bond and a hydrogen bound to the double bond. Now, even though these have similar stories, they're not identical. So this hydrogen is bound to a carbon that has a methyl group attached. This hydrogen is bound to a carbon that has an ethyl group attached. So these technically have 2 different electronic environments, which will make them 2 different protons. So we'll go ahead and call them C and D. And lastly, we have a set of 2 hydrogens in the middle of proton D and proton B. There's no other set of 2 hydrogens, so these are going to make it their own type, and we'll call those type E. So we have 5 different types of hydrogens, so we would expect 5 signals. And for our last molecule, we have 3 hydrogens, 2, another 2, and another 3. Now these 3 hydrogens are bound to a carbon that's 2 bonds away from our carbonyl. These 3 are also bound to a carbon that's 2 bonds away from our carbonyl. So we can see symmetry in this molecule, and with symmetry, that's when we can start identifying similar types of hydrogens. So these 2 sets are actually identical, so we'll go ahead and call those type A. These 2 and these 2 are also identical. They're 1 bond away from our carbonyl, so we'll go ahead and call those type B. So even though it appears that we have 4 sets of hydrogens in this molecule, the symmetry makes each set identical to one another. So we have 2 types, and we would expect 2 signals. Homotopic protons are completely identical, and the way we can tell if protons are homotopic is that we can see if a molecule contains an axis of rotational symmetry that allows one proton to be rotated onto the other without changing the overall molecule. So for example, in our first molecule here, we have an axis of rotation. So if we go ahead and draw this line of symmetry here, if we were to rotate the molecule around this line 180 degrees, this proton would become this one, and there wouldn't be any way of distinguishing one from the other. For this molecule here, we can draw a line of symmetry right through the middle. Again, if we were to rotate this molecule around 180 degrees, there's no way of telling this proton from this one. They will be exactly the same. For this molecule, we have an axis of rotation here. Again, rotating this molecule around 180 degrees, this hydrogen will easily become this hydrogen, and there's no change in the overall structure of the molecule. So if our molecules contain this axis of rotational symmetry, then it means that we have the potential to have homotopic protons. Other types of protons that are identical are known as enantiotopic. Now they are enantiotopic if the molecule contains a plane of reflection that makes one proton the mirror image of the other. So for instance, if we were to take this molecule and put a plane of symmetry through the fluorine and the chlorine, if we were to have a mirror go through all of these bonds, we would have this H be reflecting this H. Because they reflect each other perfectly, it's going to make them enantiotopic. In this molecule, we can put a plane through the ring as well as this bond. Now, if we just take a mirror and essentially chop through this ring, we would have this H reflecting this H over here. And again, since they reflect each other perfectly, it makes them anisotropic. Now, in molecules containing chiral centers, we can start to introduce different types of hydrogens that may be bound to the same carbon. So for instance, if we're going to focus on this molecule and these two hydrogens are chemically equivalent. They are the same. And in this molecule, there is both an axis of symmetry. So if we were to draw a line through here and rotate it around 180 degrees, this hydrogen would become this one. This molecule also contains a plane of symmetry. So if we were to take a plane and put it straight through the middle of all of these carbons in these two rings, this H would reflect this H. So we have two reasons that these hydrogens are chemically equivalent. However, if we were to take this molecule and introduce a chiral center here, now this chiral center shows that we have an OH that's pointing down below the plane of the ring. So what that's going to do is it's going to change the electronic environments of these two hydrogens. The hydrogen that's on the same side, or cis, to the OH group is going to have one chemical environment, whereas the H that's on opposite sides or further away from the OH group will have a different electronic environment. So even though these H's can appear to be the same, they are not interchangeable because of their proximity to the OH group. Chemical shifts tell us about the electronic environment of the protons in the molecule. Now with chemical shifts, we want to see if the protons are surrounded by a lot of electron density or not a lot of electron density. Now all protons will always be compared to a standard, which is TMS. TMS stands for tetramethylsilane. It's this structure here. And this is considered, the hydrogens in these molecules are considered the most shielded protons in organic structures. So there's a lot of electron density surrounding all of these protons. So that means every other organic molecule will have protons that are slightly less shielded than these. So the way that the chemical shift is calculated for a set of protons is a machine will take the observed shift from TMS, and this is measured in hertz. Then that's divided by the operating frequency of the instrument in hertz. Now this little delta sign indicates chemical shift. So for example, if we were to take benzene and measure it on a 300 megahertz instrument, we would get a chemical shift of 2181 divided by 300 times 10 to the 6 hertz. Ultimately, this is going to come out to 7.27 times 10 to the minus 6. The key chemical shift number that we're always going to focus on is 7.27. And to be more specific, it would be reported as 7.27 parts per million. So that would incorporate the times 10 to the minus 6. So these are the types of numbers that we're going to see associated with a chemical shift for different types of protons. So most chemical shifts will appear between 0 and 12 ppm. Now this is an example of an NMR spectrum. So the 0 will always be on the right, and TMS is always going to have a ppm of 0. So if you ever see a peak on an NMR spectrum exactly at 0, that will represent the standard TMS. Now, any protons that give peaks that are close to TMS at low chemical shifts, this is known as the upfield region on the NMR spectrum, and it represents shielded protons. Shielded protons are less affected by the external magnetic field. And they also have a small delta E between their alpha and beta spin states. Over here on the left, further away from the TMS standard, this is known as the downfield region, and any peaks that appear here will represent de-shielded protons, or essentially protons that are more affected by the magnetic field. So the protons that come up in this area have a larger delta E, so a larger amount of energy that's necessary to flip back and forth between that alpha and beta spin states. Now, as far as chemical shifts go, alkane protons generally give signals around 1 to 2 ppm. So they're very close to TMS, which means that alkane protons in general are very shielded. Now, if we take alkane protons and put atoms that are electron withdrawing or electronegative, it can shift the chemical shifts for those protons downfield because the electronegative atoms pull the electron density towards themselves and cause more de-shielding for those protons. So for example, with methane, which is just a basic alkane, we would normally expect to see a chemical shift for these hydrogens to appear at around 1.0 ppm. Now, if we introduce iodine, which is a little more electronegative than the carbon and hydrogen, the iodine is going to pull some of that electron density towards itself and make these hydrogens more de-shielded. As we get more de-shielded, we're going to increase the chemical shift to about 2.2. Now, skipping all the way up to fluorine. Fluorine is the most electronegative atom. With fluorine, we have such a pull of the electron density towards the fluorine atom that we see a huge shift in the chemical shift to about 4.3 ppm. Now, the number of atoms can also influence the change in the chemical shift. So the presence of one chlorine in the molecule will change the shift from 1.0 for these protons all the way up to 3.1. With two chlorines, you have double the atoms pulling the electron density towards themselves, and you have double the de-shielding effect. So we see an increase to about 5.3. Three chlorines are going to pull so much electron density from this hydrogen here that we see a change in the chemical shift to about 7.3. Now, the proximity of the electronegative atom does influence how much the chemical shifts are going to change. So for example, the hydrogens on the alpha carbon, meaning the carbon containing the electron withdrawing or electronegative atom, these protons will show the largest effect from this electronegative atom. So these hydrogens will show a peak at around 3.3 ppm. Now these two hydrogens, which are on the beta carbon, so the second carbon away from our electronegative atom, they are further away from this electron withdrawing effect, and so there's less of an effect on the chemical shift. So we see a shift of about 1.6. These three hydrogens, which are on the gamma carbon, are so far away that this chlorine actually can't influence them at all. So they have their peaks appear at their normal chemical shift of around 0.9 ppm. So the further away you get, the less of the effect of the electron withdrawing or electronegative atom. Table 15.1 in the book actually allows us to calculate the effect of different groups on the alpha protons. So for example, if you have your alpha protons that are right next to an oxygen, such as an alcohol or ether oxygen, the oxygen is electronegative, so it's going to pull electron density towards itself. Now, anytime you have these hydrogens on that alpha position, you can add 2.5 ppm to where the chemical shift would normally appear. So for example, a CH2 group, which is known as a methylene group, normally has a peak appear around 1.2 ppm. But by placing this methylene group right next to an oxygen, we add 2.5 to that chemical shift, and that means we would expect to see a peak for those hydrogens at around 3.7 ppm. Now, if we were to actually take this molecule and run it in an NMR machine, we would see peaks appear at 3.7. Now, when the oxygen is connected to a carbonyl, such as in an ester functional group, here we have double the electron withdrawing effect. we have our electronegative oxygen, and we also have an electron withdrawing carbonyl group. So we would see a larger effect on the chemical shift with positive 3. So again, normally CH2s or methylene groups come out at around 1.2, but because these are right next to an ester, we are going to have positive 3 added to that chemical shift. So we would expect to see a peak at around 4.2, representing these hydrogens here. And in fact, if we were to take this molecule and run it in the NMR, we would see the actual chemical shift around 4.1. So these are very close. Lastly, if you have alpha hydrogens right next to a carbonyl, now a carbonyl, because the oxygen is further away, it has less of an electron withdrawing effect than when you have the oxygen directly attached to the alpha carbon. So we would see a lesser effect by adding only 1 to the typical ppm. So again, these guys normally come out at around 1.2. If we add a carbonyl to the molecule, we would add 1, and we would expect to see the peak at around 2.2. And in fact, in this particular molecule, we do see a peak at around 2.4, which is very close to our 2.2. Now, you would never be expected to do these calculations on an exam, but it does help you see how the proximity of these electronegative atoms can influence the chemical shifts. Now, this chemical shifts sheet is available on Canvas, and it's something that you will be able to use on exams. So I'm just going to walk you through this sheet. It's showing the chemical shifts for different types of hydrogens that could appear in a molecule. So first things first, we have our TMS, which is just our standard, and it's always going to be at 0. These 3 groups are our base alkane hydrogens. So we have a methyl group, which typically comes out at around 0.9 in just a regular alkane. We have our methylene group, or our CH2 group, which typically comes out at around 1.3. And then we have our methine group, or CH, and these typically come out at around 1.4. Now, all of these other chemical shifts are just showing different types of hydrogens in different scenarios. So for instance, if you have a methyl group, and we're focusing on these hydrogens in this methyl group here, directly connected to a C double bond C, we're going to see an increase in the chemical shift from around 0.9 to 1.7. If we have a methyl group right next to a carbonyl, just as we saw on the previous slide, we would see an increase in the chemical shift to about 2.1. Having a methyl group attached to a benzene ring would have a chemical shift of around 2.3. So for each of these chemical shifts, we're focusing on all of the hydrogens that are shown. So you can go ahead and underline them or circle them because that's what we are going to be focusing on. But all of these chemical shifts represent the changes that occur from these base numbers with the presence of different types of groups. Now for these guys over here, we'll talk about amines, alcohols, phenols, and carboxylic acids in just a little bit. With these, they tend to have variable chemical shifts depending on the conditions that the NMR is taken in. So this just tells us where you can approximately find a chemical shift representing the hydrogens that are connected in an amine, an alcohol, a phenol, and a carboxylic acid. An important type of hydrogen to easily recognize are the aromatic protons, meaning the protons that are directly connected to a benzene ring. Now, aromatic protons are very deshielded, so they come out around 6.5 to 8 ppm. There's very few protons that will appear in such a high ppm or a high chemical shift. So it will be important to recognize that looking at that 7 to 8 region, if you see any peaks there, it's going to represent an aromatic proton. Now, other types of protons that appear at high ppms are aldehyde protons, so the H directly connected to a carbonyl. This comes out at around 9 to 10 ppm, so it's even more deshielded than an aromatic proton. And also carboxylic acid protons, specifically the one directly connected to the oxygen. These come out at around 10 to 12 ppm. So these are the main types of protons that appear at very high chemical shifts. Most other types of protons will appear at chemical shifts less than 8 ppm. Next, we're going to talk about integration. Now, the integration is the area under the peak, and it correlates with the relative number of protons giving rise to a signal. Now, for the most part, this is going to be done for you, and I'll show you how it looks in just a little bit, but I just want to explain how these numbers come about. So typically, an NMR machine will give a certain integration that comes from the area under each of the peaks. So these are the integration values that come from each of these peaks. Now, a chemist will set one of these peaks to a whole number to let it represent a number of protons. Then the computer can do some calculations and the integration ratios to set values for the other peaks. So the way that this is going to work, a chemist would choose the peak that has the lowest integration value. So this is going to represent the peak that has the fewest number of hydrogens. So we will go ahead and call this peak 1 hydrogen because that's the fewest number of hydrogens you can possibly have. Now what the computer will do is they'll take this value and divide it with all of these other numbers. So we'll end up with values of 1, 1.5, 1, and around 1.5. Now, since you cannot have 1.5 hydrogens, we have to adjust the integrations so that the number of hydrogens represent whole numbers. So what we're going to do is take the numbers that we just saw in the previous slide and we're going to multiply them by 2. So now we have a ratio of 2 hydrogens, 3 hydrogens, we can go ahead and round up to a whole number, 2 hydrogens, we'll round down, and 3 hydrogens, rounding down. Now the way that this is often going to be presented to you in the NMR data that you see is you will see above a peak 2H, or just the number 2. And these numbers just above the peaks represent the number of hydrogens that give rise to that particular signal. So this is typically what you are going to see, but you just saw the method that gives us those numbers. Now, integrations don't always give us the exact number of hydrogens in a molecule. Instead, they're going to give us the relative quantities. So, integrations give us a ratio of molecules. So, molecules that are symmetrical, the symmetry can affect the integrations. So in this molecule, 3-pentanone, we have 2 sets of 2 hydrogens that are identical and 2 sets of 3 hydrogens that are also identical. Now the computer is going to focus on one of these complete sets only. So once the computer goes through the process of determining the integration, we would see 2 signals that have a 2 to 3 ratio. Now that's not going to correlate exactly with the actual number of hydrogens, which is actually 4 to 6. So in the next slide, we'll see how we know, based on NMR data, if the molecule has symmetry or not. So this is an example of the actual NMR for 3-pentanone. Now, after the integration is calculated and analyzed, we would end up with 3 hydrogens above this peak and 2 hydrogens above this peak. Now, in order to know that this molecule is symmetrical, you either need to have the exact molecule or you must know the molecular formula. So the molecular formula for our 3-pentanone is C5H10O. So here we can see that this molecule contains 10 hydrogens. So if we see on the NMR spectrum a total of 5 hydrogens, This is going to indicate to us that there is symmetry in the molecule, and there's one axis or one plane of symmetry where these numbers can be doubled. So you either have to know the structure of the molecule or the molecular formula in order to determine if symmetry is a possibility.